In the last lecture, we started talking about the errors that might arise in quantum communication. We found that, like in classical communication, one could of course have a situation where the amplitude of the qubits are being changed, the relative amplitudes of various basis states will be changed. But in addition to that, there is also a question of the relative phase between the various members being changed. Now, what we want to do today is to talk about steps that could be taken in order to correct these things. I had already explained last time that the option of sending multiple qubits and deciding which is the correct one by a majority vote, as is done in case of classical bits, is not really an acceptable alternative because of the quantum no cloning theorem, which precludes multiplication or repetition of states. We will talk today about an error code and the possible steps that one could take. And I must alert that this simple-minded code that I will be talking today is not a complete code in the sense that while it takes care of the correction of amplitudes, that is correction of bit flips, it doesn't quite take care of changes in relative phases of in case of a superposition. So, let us see, I again use this phrase that suppose I have a sender whose name is Alice and I have a receiver whose name is Bob, and let us see how does this communication work. Now, Alice wants to send a state psi. So, this is Alice's protocol. We have seen that Alice cannot duplicate this state, but let us see what Alice can do. So, this is some state psi, which is, in my example I will use it as some alpha 0 plus beta 1. So, let me write it here. The state psi is alpha 0 plus beta 1, properly normalized so that mod alpha square plus mod beta square equal to 1. What Alice does is to introduce two ancilla. These ancillas are initially set to 0. Then she executes a quantum circuit of this type. And whatever comes out here is what we will call as psi logical. This is what will be sent through a communication channel. Now, look at what is this situation. Since this state psi is alpha 0 plus beta 1 and these two states were zeros each, what I get here, so I initially start with this is the second bit, this is the third bit. In this case, the control is 0. So, therefore, at this stage, when I do this operation, I first get alpha 0 0 plus beta. Now, the control is 1 for this bit. So, therefore, this will make it 1. So, I will get 1 1, and of course, the third bit has not yet been changed. So, it remains 0. In the third case, the second bit is used as a control. So, I get alpha 0, since the second bit is 0, third bit remains 0. But when I come to this term, my second bit is 1. So, I get beta 1 1 and this 0 will be flipped to 1. So, this is my psi logical. This is very similar to what we had in classical bit, excepting it is not the repetition of psi, 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 but psi has this structure and it has sent this. Now, I have a noisy channel which flips a bit, and let me say it flips with certain probability p. So, noisy channel flips a qubit with some probability p. And leaves a bit unchanged with a probability obviously which is 1 minus p. This will give me this situation as is shown in the table, but I will take a bit of a time in explaining some terms there. So, first is the possibility that I had alpha 0 0 0 plus beta 1 1 1 and Bob receives it without any change, which means each of the 3 qubits have been left untouched. So, the probability of that happening is obviously 1 minus p cube. Now, let us look at this single qubit flip situation. Now, suppose my first qubit is flipped, then my state will be 1 0 0 plus beta 0 1 1 when you flip the first qubit, and the probability of this happening will be clearly p times, because that is the probability of a flip, into 1 minus p square. And not only this would be true of, for example, second qubit flip 0 1 0 plus beta 1 0 1, or third qubit flip which is 0 0 1 plus beta 1 1 0, and in each case the probability is this. So, the total probability of a single bit being flipped is 3 times that. The situation with respect to 2 qubit flips. Now, if 2 bits are being flipped, then it could be 1 2, 1 3 or 2 3. So, I can get, if 1 2 gets flipped, 1 1 0 plus beta 0 0 1. If 1 3 gets flipped, I get 1 0 1 plus beta 0 1 0, and if 2 and 3 get flipped, I get alpha 0 1 1 plus beta 1 0 0. And the probability of such a thing happening in each case is p square into 1 minus p. So, therefore, I get 3 times p square into 1 minus p. And finally, the probability that all the 3 bits get flipped gives me the state alpha 1 1 1 plus beta 0 0 0, and that would happen obviously with a probability of p cube. And this is what the slide here indicates. Okay, having done that, let us look at what can Bob do. Now, Bob knows that there is a probability with which the noisy channel is working, and so what he has received is what I showed in that table. Now, when Bob receives this, Bob does certain other operations. Bob at his end adds, let me first draw lines corresponding to the bits received. So, we have been calling this psi logical. Bob adds 2 ancilla qubits which are initially set to 0, and Bob executes the following operations. The first thing that Bob does is to use the first qubit as the control and apply a C0 gate on the first ancilla bit, Then he uses the second line as the control and again does the same thing to the first ancilla bit. For the second ancilla bit, his operations are slightly different. The reason we will see here little later, and this is he uses the first as the control and the third as the control to execute C0 gates. Now, so at this stage, the situation here is I still have the psi L because we have not disturbed them, but in this case the ancillas have been disturbed. So look at the slide for the picture of the circuit. Now, so what is happening in this slide is this, that the ancilla bits have been changed by whatever I illustrated just now, and this situation comes here. I will work out how does the ancilla change, but at this stage Bob will do a measurement, and depending upon the state of the measurement, he will do some corrections on the bits that he has received. So let us look at what Bob does and what are the possible results of Bob's operation. So Bob's operation will now generate what we will be calling as psi 3. So psi 2, which was the state of the situation which Bob received, they were, as we have given, 8 possibilities we had given. So this was alpha 0 0 0 plus beta 1 1 1. I had given some probability with which it occurred, and let us look at this situation here. Now in this situation, when Bob executed this, what happened? Come back here and then we'll, so my ancilla states were 0 0. Since Bob decided to use the first and the second as the control to change the first ancilla bit. In this case, the first control was 0, so that kept this 0 as 0, second control was also this 0, so therefore nothing happened to this. So therefore I would write this as this happened alpha 0 0 0 and 0 0. But let us look at what happens to the second term. So this will be, now remember first and the second qubits are the control for the, so far as the first qubit is concerned. So because this control bit is 1, it will flip this 0 to 1. But the second control bit, which is also 1, will flip it back to 0. So therefore what I will get is beta 1 1 1, which is the control which is always left alone, times 0 0. So in such a situation, I will have alpha 0 0 0 plus beta 1 1 1 times 0 0, that is ancilla bits are not affected at all. And you can check that the situation with respect to the second qubit is also the same, because any time the two control bits are 1, then there is a double flip. So original bit flip that took place after the first C0 gate is cancelled because of the second flipping also. But this of course is a very special case, but let us look at one of the other cases. So let us say that in the second case we had said with a probability of p into 1 minus p square, I am likely to get a state like this. There are 3 of them, but let me illustrate it with only one of them first. So I had this situation here. Now what do I get? So my control of C0 is the first and the second. Now you notice that I have a 1 and a 0. So this will give me alpha 1 0 0. So far as this qubit is concerned 0, that will be flipped. So I will get 1 there. Now remember that the second ancilla bit is being controlled by the first and the third, and here I have a 1 and a 0 there, so the second one also gets flipped. Plus beta 0 1 1 the C0 control was the first and the second qubit for the first qubit. So there is a 0 and there is a 1, so that must flip it. So therefore I get it 1, and the control for the second qubit was the first and the third, so which is also going to make it 1 1. Again notice that what I got was 1 0 0 plus beta 0 1 1, which is what I received times 1 1. The ancilla bits got changed naturally because I am doing operations on ancilla, and the complete list of what we receive, what the states are after Bob has done these operations is given in this table. If a look at this table, which is little clumsy because there are too many items there, will convince you the following, that as a result of the operations that we did on the two ancilla bits, the first ancilla bit with the first and the second line as the control, and the second ancilla bit with the first and the third line as the control, will change the ancilla bits in such a way that the ancilla bits state in both these terms happens to be the same. So look at these and remember that these had different probabilities associated with them. So in the first three cases here, I had P1 minus P square as the probability. In this case it was this, and final was PQ. But at this stage, if I measure an ancilla, the ancilla bit, I am likely to get either 0 0 or 0 1 or 1 0 or 1 1. Each of these terms come in two terms. So let us look at what happens to the case where my ancilla bit is 0 0. If you look at it, this line, the first line has 0 0 1 1, and the last line also has the ancilla bit as 0 0. But there is a difference. In the first case, the first three lines have been unchanged. This probability was 1 minus p cube, but in the last line we realized that this is not what Alice sent, but this is what Bob received with the probability p cube. And so therefore, in this case, if ancilla state is 0 0, Bob takes no action, but then his states are as received without any error with a probability 1 minus p cube, but received with error in all the three bits with a probability p cube. Now let us look at, supposing the ancilla bit was 0 1. I will not do all of them, but mine is the illustration. Look at where is 0 1 for the ancilla bit. So my ancilla bit is 0 1 in this case, which is alpha 0 0 1 plus beta 1 1 0. This gives me 0 1, and there is also this other case which is alpha 1 1 0 plus beta 0 0 1. Both these terms had 0 1 as the ancilla bit, but this one came with a probability of p into 1 minus p square, but this one came with a probability p square into 1 minus p. Now this means that Bob received with one error this situation and with two errors this situation. So what Bob does, if he receives either of them, is to apply an X gate, that is a sigma X operator, on the third qubit. Now, if Bob applied sigma X or the X gate on the third qubit, this state will become alpha 0 0 0 plus beta 1 1 1 as is expected. So, the states which were received with errors p into 1 minus p square will be corrected. But this will make this state alpha 1 1 1 plus beta 0 0 0, which has been received with a probability p square into 1 minus p. This is of course wrong. Look at the slide again. If the ancilla bit is measured to be 1 0, ancilla state is 1 0. Again, there are two places where such a thing happens. This is alpha 0 1 0 plus beta 1 0 1 with 1 0. Now, what Bob does in such a case is to apply sigma X or the X gate on the second qubit. That will make it alpha 0 0 0 plus beta 1 1 1 as was sent, and that we have seen was again something which had a probability of 1 minus p into 1 minus p square. But the second alternative that was there, where the second qubit was 1 0, was alpha 1 0 1 plus beta 0 1 0. If you apply second X gate on the second qubit, it will get alpha 1 1 1 plus beta 0 0 0, and this state, as we know, appears with a p square 1 minus p probability. So, in other words, once again, Bob's action has been to correct the error that occurred in the second qubit, or he was able to correct it with a probability p into 1 minus p square, and he still has an error which occurred with a probability p square into 1 minus p. Finally, if ancilla was measured to be equal to 1 1, then this X gate X is applied on the first qubit, and you can work it out easily to check that this application would once again correct the third qubit position, which was received with the probability of p into 1 minus p square. But then the other state which had the same value of ancilla, which has the probability of p square into 1 minus p, that does not get corrected as before. So, out of the 8 cases, in 4 cases it will be corrected, and the other 4 cases will continue to have error. So, let us look at how many of these states continue to have errors. So, firstly, the probability of that happening is 3p square into 1 minus p plus pq. These states are this is the total correction. So, if you add it up, it becomes 3p square minus 2p cube, which is less than p. If p is less than half, supposing p was equal to 0.01, you can calculate it. You will find that those cases which is not, where it is not corrected, is with a probability of 3 into 10 to the power minus 4, which is a great improvement, because what we have found is that we have been able to reduce error by a factor of 300. So this is the way a 3-qubit code is able to recover error to a great extent.